Okay, hello. We are back and we're going to continue with this problem here. This is the raindrop problem, I guess. So we're told that a raindrop is a perfect sphere. So let's go ahead and kind of get started here. And here we go. This is better. So we've got a perfect sphere and the radiuses are. So one of the formulas that we need to know, so here that I'll just put this in facts we need to know in order to do this problem. Facts we need to know. First thing we need to know is the formula for surface area, because we're told that the surface area is S centimeters squared. So in general, surface area, the formula for surface area is 4 pi r squared. Okay, so if we are told that the surface area on the one hand is equal to S, and on the other hand it's going to be 4 pi r squared, we can conclude that 4 pi r squared is equal to S. Okay. Now another fact we need to know is, let's see here, condensation accumulates on the raindrop at a rate equal to K times S. So the rate that condensation accumulates is going to be rate that condensation accumulates is going to be the same as the rate of change of the surface area. Condensation accumulates because the rain is going to accumulate on the surface of the raindrop. On surface of raindrop is the same as change in surface area over change in time. So then I would say d surface area dt. So d dt of the surface area. Now over here, if we know that S is equal to 4 pi r squared, that means that d dt of our surface area is going to be d dt of 4 pi r squared, which is going to equal, let's see here, so we'll have 4 pi and then 2r r prime. So I have a total of 8 pi r prime is our surface area prime. And we're told in the problem that this derivative with respect to time of surface area is equal to K times S. So let's put it all here. So we're told that K times S is equal to the derivative of the surface area, and the derivative of the surface area with respect to time is 8 pi r prime. 8 pi r prime. But we're also told that S is equal to 4 pi r squared, right? Because S is the surface area, and we know our general formula for surface area is that it's 4 pi r squared. So we'll have K times 4 pi r squared. So from here, we must have that this is equal to this. So let me actually go ahead and make it. Okay, so K times 4 pi r squared is equal to 8 pi r prime. Okay. So I can, let's see here, so K times 4 pi r squared minus 8 pi r prime is equal to 0. So I just subtracted 8 pi r prime from both sides. And now I'm going to factor out 8 pi r. Sorry, I'll factor out 4 pi r. Ooh, that was big. This is a k. So I'm going to factor out 4 pi r. And I'll be left with rk minus 2r prime equals 0. So this tells me that either 4 pi r equals 0 or kr minus 2r prime equals 0. So either r is equal to 0, in which case we don't have a raindrop, we just have a dot. Okay, so this is what's called a trivial case, because you no longer have a raindrop, you have just a point. And now over here, we would get that r prime is equal to k over 2 times r. Okay, so show that the radius of the raindrop increases at a constant rate and find that rate. So we have found the rate at which the radius increases, and the radius increases at the rate of k over 2 times the original radius. Okay. All right. Okay, let's go to this problem. The length of each side of a cube is increased at a constant rate. So the first thing I'm going to do is draw my picture of a cube. Okay. It's kind of messed up, but there you go. This is getting worse. Okay. So this is close enough. I've got my cube, and I'm asked which is greater, the relative rate of change of the volume of the cube, which is v prime over v, or the relative rate of change of the surface area of the cube, which is a prime over a. So the question is, which is greater, v prime over v versus a prime over a? Okay, so if I have this is a cube. Now notice here they're telling us that A stands for the surface area, right? The surface area. So A stands for the surface area, and V stands for the volume. That's pretty typical. So what I need is formulas for the surface area. So the A, which is the surface area of the cube, is going to be surface area of the cube is going to be 6 times s squared, because we'll have 6 surfaces, right? So we'll have the 6 faces, right? 1, 2, and then 3, 4, and then we'll have the top 5, 6. So I have 6 times s squared, and the volume of the cube is going to be just s cubed. So v prime over v is going to be equal to, let's see here, v prime over v is 3s squared, s prime. Now v is s cubed. Okay. We'll be able to cancel some things out, and we'll just get 3s prime over s. The area, the surface area, a prime over a, is going to equal, now I'm back up here with my surface area is 6s squared. So the derivative with respect to time of the surface area of the cube is going to be 12s s prime. And in the denominator, I put the area, the surface area, which is 6s squared. So I actually will get 2s prime over s. Okay? So if I'm comparing v prime over v versus a prime over a, the relative rate of change of volume is 50% larger than the relative rate of change of surface area, because v prime over v is equal to 3 times s prime over s, and a prime over a equals 2 s prime over s. So v prime over v is 50% greater than a prime over a. Okay. All right. And this is the last one. So this question here says that sand falls from a hopper at a rate of 0.1 cubic meters per hour. Okay, let's start. So if we have a hopper, which is some kind of, I don't know, machine, right? And sand is falling out of it, and the sand is falling out in the shape of a cone, a pyramid, right? A conical pile is what we're told.
It's
Conical
21:15.
pile. Okay. So let's see here. So sand falls from a hopper at a rate of 0.1 cubic meters per hour. So 0.1 meters cubed per hour. Let's just call that equal to x prime. It's equal to the rate at which the volume of sand in pile increases. So instead of using x prime, let's actually use v prime. And v, of course, is going to equal the volume of sand in pile after t hours. Okay, so we've got two variables set up here, one variable actually. We're keeping track of how much sand is in the pile after t hours. So perhaps in the beginning, right, we've just got a little teeny tiny sand. Like maybe this is after 1 hour, right? It says t equals 1. But then after, I don't know, 10 hours, perhaps the pile looks bigger. So the pile always is in the shape of a cone. And the issue is the volume of the cone increases as time increases. Okay, so if the side of the cone makes an angle of pi over 6 radians with the vertical, okay, so now we're focusing on this cone, and we're saying that from here to here, we've got an angle of pi over 6. Okay, so we've always, regardless of the size of the pile, have an angle of pi over 6 radians. Find the rate at which the height of the cone increases. So I want h prime, which is equal to rate at which height of cone increases. So that tells me that I need h as another variable, and h is going to be the height of my cone at time cone after t hours. Okay. So in my picture, h is going to be the altitude of this triangle. And I know that the volume, let's see what we can play with here. If I know that the volume is, I can find a formula for the volume based on the height and the radius, right? So I'm trying to now find the relationship between V, right, and H. And I know that in general, I can find the volume as a function of height. So is 4/3 pi r squared times the height. And now r is the radius, which would be the other leg. Volume of a cone. Oops, sorry. It is pi r squared h. There's no factor of 4. Let me delete this factor of 4. So it should just be 1/3. Okay. So how can I find the r radius if I know that the radius as a function of height, if I know my angle is pi/6? So going off of my triangle here, it must be that tangent of pi/6 is equal to h/r. So since we have the angle always equal to pi/6, tangent of pi/6 is equal to h/r. So r tangent pi/6 equals h. So r is equal to h over tangent of pi/6. Tangent of pi/6 is equal to tangent of pi/6 is equal to we'll find tangent of pi/6 later on. In the meantime, I'm just going to substitute h over tangent of pi/6 into my formula here. So I can write that this volume is going to equal 1/3. In fact, I can combine the pi and the 1/3 to pi/3. And now instead of r squared, because r is h over tangent of pi/6, we'll have h over tangent of pi/6 squared, and then times that h. Okay, and so this is, so we figured out that tangent of pi/6 is √3/3. Okay, so we've got that squared times h, which is equal to pi/3 times, so we'll have h squared over, and on the bottom I will just have 3/9, okay, times h, okay, which is equal to, I have a pi h cubed. I'm going to multiply the top and the bottom by 9. So 9 is going to cancel out with that 9. So I have a 9 on top and a 3 and a 3, which is a 9 on bottom. So I'll just have pi h cubed. All right. Okay, so I just have pi h cubed. So this is my relationship. So it took us a while to figure it out, but the relationship between my variables is very simply volume equals pi h cubed, right? So now I'm ready to differentiate. Now how do I differentiate? I'm going to differentiate with respect to time. So I'll get v prime equals pi times 3h squared h prime. Okay. And now, I believe, let's see here. We're given that sand falls in the hyperborean rate of 0.1. So I'm down here and v prime is equal to 0.1. So 0.1 is equal to pi times 3 times h squared h prime. And the question is, at what rate, well first, if the side of the cone makes an angle of pi over 6 radians with the vertical, find the rate at which the height of the cone increases. So we want to find h prime. So here, h prime, we're just going to solve for h prime. Right, so we're going to divide both sides by 3 pi h squared. Now remember, you always want to check when you're dividing that you're not dividing by 0. And in this case, it makes sense. We're going to put in here assuming that h is bigger than 0, because this is okay, because if h is equal to 0, then we really don't have a pyramid, right? So it's okay to just put in there that we're assuming that h is a positive number. That way we're not dividing by 0. And we get that h prime is equal to 0.1 divided by 3 pi h squared. So this is one formula that gives us the rate of change of the height of the cone. Okay. And now at what rate does the radius of the base increase? Okay, so at what rate does the radius of the base increase? That means we need to find r prime. So we're going to use this formula here. If r is equal to h divided by the tangent of pi over 6, which we said is h over root 3 over 3, which is just root 3 times h. This means that r prime is going to be root 3 times h prime, right? So we can use the fact that we found h prime to be 0.1 times, or 0.1 divided by 3 pi h squared, to say that our r prime is going to be root 3 times that. Okay, so these answers together are a solution. Give both answers in terms of h, the height of the pile in meters. Okay, and we can go back and verify that our units align, and they do. Okay, so for here, our units h prime will be meters per hour. Okay, and the r prime will be meters per hour. Again, the units for V is going to be in meters cubed, and everything's good. Okay,